Question 4. This question is about S-block metals, so that's metals in group 1 or group 2. Give the full electronic configuration for the calcium ion Ca2+. Well, calcium has got an atomic number or a proton number of 20. So it's got 20 protons and 20 electrons. If it's 2+, it's lost 2 electrons, so it's got 18 electrons. It's lost its 4s electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6. 2 add 2 is 4, add 6 is 10, add 2 is 12, add 6 is 18. So it's had 20 electrons when it was an atom, lost 2 electrons, and now got 18 electrons. It's lost its 4s electrons, so you can just leave that off if you want to. Explain why the second ionization energy of calcium is lower than the second ionization energy of potassium. Well, calcium is a much larger atom, so if it's larger, because it's further down the periodic table, then its outer electrons are further from the nucleus. Remember, it's the nucleus that provides nuclear attraction for the electrons, so the further away there's less nuclear attraction. Also, there's more shielding in calcium because it's got more electron shells. It's further down the periodic table. Identify the S-block metal as the highest first ionization energy. So it's something towards the top, something that's small, because if it's small, the electrons are closer to the nucleus, and the attractions of the protons in the nucleus. So right at the top of group 1 and group 2 are lithium and beryllium. So the answer is actually beryllium. Beryllium because it's to the right, it's right of lithium along the second period, and therefore it's got more protons. So as you go across a period from left to right, the general trend is that the atoms get smaller and the ionization energies go up, because the smaller atoms higher first ionization energies, because more protons mean more nuclear attraction as you go left to right across the period. Give the formula of the hydroxide in group 2 from magnesium to barium that is least soluble. So magnesium hydroxide is the least soluble, and it's MgOH2. So the formula MgOH2, magnesium is in group 2, OH is a 1- ion, so 2+, magnesium forms a 2+ ion because it's got 2 electrons in its outer shell that it wants to get rid of. To become stable, OH-, 2+, minus, I need 2 OH minuses to balance up the charges. A student added 6 centimetres cubed of 0.25 mole decimeter cubed of barium chloride to 8 centimeter cubed of 0.5 mole decimeter cubed sodium sulfate. Show by calculation. Well, even before I work out what it's asking me, I know that I'm going to do concentration. 0.25 is moles divided by volume in decimeter cubed. So I'm going to divide the 6 by 1000 to get 0.006. Concentration 0.25 equals moles divided by 0.006. And then I multiply the two together and it comes out as 1.5 times 10 to the minus 3. Number of moles of sodium sulfate, again I take the 8 centimeter cubed and I divide it by 1000 to get 0.008 centimeter cubed. Concentration 0.15 is moles divided by 0.008. Multiply the 0.008 or 8 divided by 1000 multiplied by the 1.5 gives you the number of moles of sodium sulfate. Which one's in excess? Well, which one's the larger value is barium chloride. So barium chloride is in excess. Just to go back to this one, the ionic equation of barium and sulfate. Barium is a 2+ ion because it's in group 2, so it'll form lose 2 electrons, become 2+. The sulfate ion you need to learn is SO4 2-. When the two come together, the 2+ and the 2- cancel each other out, and so it's BaSO4. Total volume of the other reagent. So what that's asking is how much sodium sulfate would I have to add for the barium chloride not to be in excess. That's broadly what it's asking. So how much more of this would I have to add to make 1.5 times 10 to the minus 3? So subtract these two, and so I work out that I need 0.003 moles of sodium sulfate, so that these are in equal amounts. Concentration is moles divided by volume. The concentration of the sodium sulfate is 0.15. The number of moles that I need to add is 0.003 divided by the volume. So the volume is 0.003 0.003 divided by 0.15, which is 0.002 decimeter cubed. To get decimeter cubed into a lower unit value like centimeter cubed, I can multiply by 1000. So 0.002 multiplied by 1000 is 2 centimeter cubed that needs adding. Now if you read the question carefully, it says calculate the total volume of the other reagent which should be used. So I've added 8 to start off with, 8 centimeter cubed sodium sulfate. I need another 2 centimeter cubed, so you've got to add 10 in total. A sample of strontium has a relative atomic mass of 87.7 consists of 3 isotopes, 86, 87 and 88 Sr. In this sample, the ratio abundances of Sr 86 to 87 is 1 to 1. In other words, they're in equal amounts. State why the isotopes of strontium have identical chemical properties. That's because they've all got the same number of electrons in their outer shell. Same number of electrons. Calculate the percentage abundance, that means how much of it there is, of the 88 strontium isotope in the sample. So I'll do spoilers on this and then you can see. So what I need to do first of all is, if the percentage of 86 strontium, let's say it's X, then the percentage of 87 strontium is also X because they're in equal amounts, so in a 1-to-1 ratio. So the amount of 87 is, everything's got to add up to 100%. So 100% take away the amount of SR86, take away the percentage of SR87. So it's 100 take away X, 100 take away 2X. Now we imagine that we add 100 particles, yeah, and out of the 100 particles, then X number of particles would have a mass of 86. X number of particles would have a mass of 87, and 100 take away 2x would be the number of particles that have a mass of 88. To work out the mass of the 86 particles, I multiply 86, that's the mass of one particle, by however many there are. 87 is the mass of the next strontium particle, multiplied by the mass by the number that they are, x, and 88 multiplied by the number that they are, and I divide by the total number of particles, which I've decided is 100. And that equals the average then, so I'm working out the average, that equals 87.7. Multiply both sides by 100, and then 173 take away 176 is minus 3x. Take this across the other side, so that becomes 8770 take away 8800, which is minus 30. Make both sides positive. 3x is 30, x is 30 divided by 3, that's 10%. So the abundance of the SR isotope, that's x is the amount of 86 SR and 87 SR, so the amount of 88 SR is 100, take away the amounts of the other two isotopes, 80%. A time of flight mass spectrometer was obtained spectrum was obtained for a sample of barium that contains the 3 isotopes. Which one would take the longest time of flight? So the one that takes the longest time down the tube is the heaviest. So whichever one has the highest mass number, and that's 138 Ba+. It's a plus charged ion, so the atom's made into a plus charged ion so that it can be accelerated along the tube. Question 5. Hydrochloric acid is a strong acid, ethanoic acid is a weak acid. State the meaning of the term strong acid. It means it completely dissociates in water to form H+ ions. Completely dissociates, or you could say ionizes if you prefer, in water when you put it in water to form H+ ions. Completely dissociates gets you the marks though. In an experiment, 10.35 centimeter cubed of 0.1 hydrochloric acid added to 25 centimeter cubed of 0.1 barium hydroxide. So first of all, I'm going to work out numbers of moles before I do anything. Concentration is moles divided by volume. So for HCl, 0.1 is moles divided by 0.01035, so moles is 0.01035. Similarly for barium hydroxide, 0.15 is moles divided by 0.025, so moles is 0.15 times multiplied by 0.025, 0.00375. Now, when these two react, because we're assuming they are going to react, you've got hydroxide, which is an alkali, and you've got an acid. Barium hydroxide, remember barium's in group 2. So barium hydroxide in group 2 forms BaOH2. 2 plus for barium in group 2. OH1 minus, so I'm going to need 2 of those. And it will make barium chloride, 2 plus 1 minus, so I need 2 Cl's, and water. In other words, 2 HCl react with 1 barium hydroxide. 2 HCl react with 1 barium hydroxide. So, my moles of HCl is 0.00135. So 0.1035 reacts with half the amount, 2 to 1, 2 HCl to 1 barium hydroxide. So 0.01035 moles of hydrochloric acid reacts with half as much barium hydroxide, and that equals 0.005175. So 0.00375 moles of barium hydroxide at the start. We've established that. So if the HCl reacts with 0.005175 moles of barium hydroxide, you can work out how much you've got left at the end of the reaction by subtraction, and that's 0.0032325. That's how much barium hydroxide I've got left at the end. Now 1 mole of barium hydroxide makes 2 moles of OH minus ions, because there's 2 OHs in BaOH2. 0.003235 moles of barium hydroxide makes 2 times that moles of hydroxide ions. So when 1 mole of barium hydroxide dissolves in water, 2 moles of hydroxide ions are made. So 0.003235 moles of barium hydroxide makes twice as much. That's 0.006465 moles of hydroxide ions that are made. Now the volume, when I add the 2 volumes together, the 10.35 and the 25, it's going to equal 35.35 centimetre cubed. I divide by 1,000 to get into decimetre cubed, because a small unit into a larger unit you divide by 1,000. And so concentration is moles divided by volume now. So we've got the number of moles of OH minus, we've got its volume, we've got the concentration. Then it says Kw, it's given me Kw now. Kw equals H plus OH minus concentration. If it equals 1.47 times 10 to the minus 14, then if I substitute 0.182885 for OH minus, and then rearrange H plus equals 8.0378 times 10 to the minus 14, minus log it 13.09 for a very, very strong alkali or a base. pH of water is 6.92. Give a reason why water is neutral, because the concentration of H plus equals the concentration of OH minus. So if something is only acid or alkali, if there's excess H pluses, it becomes acid, excess OH minus, it becomes alkali. Remember, water doesn't have to be 7 to be neutral. Temperature changes the pH of water. It's still neutral. Water is always neutral because H plus concentration, OH minus concentrations are the same. It's just that when you heat it up, the water becomes more acidic, so the pH comes down. Identify the oxide that could react with water to form a solution with pH 2. Remember, that's acid. So metals on the left hand side form alkaline or basic oxides, and elements non-metals on the right form acidic oxides. So we've got 2 basic oxides in aluminium oxide and sodium hydroxide, because they're on the left of the periodic table. We've actually got sand. Silicon dioxide is the main component of sand, so that's not even going to react with water. And then you've got sulfur dioxide. Sulfur dioxide, a non-metal in sulfur, that's going to be an acidic oxide, going to give something like pH 2. Reacts with water to form sulfurous acid, H2SO3. Give the expression for the acid dissociation Ka for ethanoic acid. Well, I've just written the equation out there. That's ethanoic acid. All acids make H+, so it must leave CH3COO-. If I take the concentrations of these and multiply them together and divide by the concentrations of the ethanoic acid, I get my expression for my Ka. A buffer solution contains 0.25 moles of sodium ethanoate dissolved in 500 cm3 and 0.07 moles decimeter cubed of ethanoic acid. So first of all, I'm going to work out the numbers of moles of ethanoic acid. So concentration is moles divided by volume. So for ethanoic acid, concentration is 0.07 equals moles divided by 500 cm3 up into a larger unit value of decimeter cubed. I divide by 1000, so it's moles divided by 0.5, 0.07 times 0.5, 0.035. That's the number of moles of ethanoic acid that I've got. It tells me the number of moles of sodium ethanoate that I've got, which is 0.025. It just tells me that in the equation. Sodium ethanoate makes ethanoate ions, CH3COO- and Na+ ions when it dissolves in water. So effectively this is the ethanoic acid, this is the sodium ethanoate. For HCl, I've got some values for HCl. So I've got 5 cm3 of 2 mole per decimeter cubed. So that's my concentration here equals moles divided by 0.005. So I've taken the 5 cm3, turned it into decimeter cubed by dividing by 1000. And so moles of these two numbers multiplied together, moles is 0.01. Okay, so what happens here when the HCl is added? What does it do? Well, the HCl makes H pluses. That's what it's a strong acid. It fully dissociates, completely dissociates into H plus and Cl minus when it's put into water. Completely dissociates into H pluses. So this is my HCl, my hydrochloric acid, and it reacts with ethanoate ions, these, and makes ethanoic acid. So for every 1 mole of this added, 1 mole of ethanoate ions are used up and 1 mole of ethanoic acid is made. So if I've got 0.01 moles of hydrochloric acid, it's going to react with 0.01 moles of ethanoate ions and make an extra 0.01 moles of ethanoic acid. So I need to adjust these values. The ethanoic acid amount has gone up by 0.01 and the number of moles of sodium ethanoate that the acid is reacting with has come down. So I've got my new moles now. It tells me the equilibrium constant, 1.76 times 10 to the minus 5, equals, so it equals the ethanoate ions, which are 0.045 now, which are 0.015 rather, so that should be 0.015 on the top, multiplied by my H plus divided by my concentration of ethanoic acid, 0.045, so that should say 0.015 and 0.045 on the bottom, and I resolve it and I get H plus concentration is 0.000528, and so my pH, which is minus log to the base 10 of that value, is 4.28. Question 6, we've got 2 cells with copper sulfate and copper in there of different concentrations. The initial voltage was 0.16. Explain how the salt bridge provides an electrical connection between the 2 solutions. It allows ions to move between the 2 cells. The standard electrode potential for Cu2 plus Cu electrode is 0.34 volts. That's this one here. So calculate the electrode potential of the left-hand one. So something add 0.34 volts equals overall plus 0.16. So the standard electrode potential of that one must be plus 0.118. This is going in reverse, so that becomes minus 0.18, and minus 0.18 plus 0.34 is plus 0.16. So this one is operating at 0.18. That's its electrode potential, the reduction potential. However, it's forced to go in the other direction by this cell, so this one becomes minus 0.18 to then give plus 0.16 when the two values plus 0.34 and minus 0.18 are added together. Both electrodes contain a strip of copper metal in the solution. Explain why the left-hand electrode does not have an electrode potential of plus 0.34. It's because the concentration is not 1 mole per decimeter cubed. The concentration needs to be 1 to give a standard electrode potential value. Give the conventional representation of the cell in figure 2, include all state symbols. So you've got copper going to Cu2+, and then you've got Cu2+ going to copper. So you've got your oxidation, and then you've got your reduction. You've got the solutions as aqueous and the electrodes as solids. When the voltmeter is replaced by a bulb, suggest how the concentration of copper 2 ions in the left-hand electrode changes. The concentration increases because Cu is going to Cu2+. In the right-hand electrode, Cu2+ is going to copper. It's going the other way because this is more concentrated. Reason why the EMF decreases to 0 is because the two solutions will eventually become of equal concentration as the ions move between the salt bridge. Question 7. When anhydrous, that just means dry, aluminium chloride is AlCl3 because aluminium's in group 3, so forms a 3+ ion. Chloride comes from chlorine Cl in group 7, so our minus ion gains 1 electron Cl-, so I've got Al3 plus Cl-, so I'm going to need 3 Cl- to balance up with the Al3+. AlCl3 therefore reacts with water, solution Y is formed. That's going to be hexa-aqua aluminium 3. So AlCl3 plus 6 waters to give the 6 water ligands around the aluminium. 3+ because aluminium's 3+, no charge on the waters, they're neutral, and we'll make 3 Cls. They're going to be minus ions, chloride ions from the aluminium chloride. 3+ and 3- make nothing and nothing on the left, so that balances. Give an equation to show how the complex ion Z can act as a Bronsted-Lowry acid with water. So you've got the complex ion, the hexa-aqua aluminium 3 ion, you've got plus water, and a Bronsted-Lowry acid means it donates H+. So the water is going to become H3O+, and the aluminium loses one of the waters. One of the waters, so I get 5 waters now, one of the waters loses an H, so instead of H2O it's just OH. And that becomes 2+. The water has gained the H+ and become H3O+, and this is 2+. 2+ and 1+ make 3+ to balance up with the 3+. The other way of looking at it, I suppose, is that aluminium is Al3+. No charges on the water, they're neutral. OH minus a hydroxide, and OH is a minus, and so 3+ and 1- make 2+. Excess sodium carbonate solution added to Y. So what happens is the AlH2O reacts with the sodium carbonate. We know this is acidic, it's a Bronsted-Lowry acid, it releases H+. And what does sodium carbonate do with acids? Well, it releases carbon dioxide, and it's going to make a white solid. What actually happens is 3 of the waters now turn into OHs, so you end up with AlH2O3OH. This has no charge, and because it's got no charge, it's a solid. So I get aluminium hydroxide as a white solid or a white precipitate. I get bubbles, that's my carbon dioxide because I've got sodium carbonate with acid. We know this is acid. And the equation, difficult equation this, you've got to remember that a carbonate ion from sodium carbonate is CO3 2-. This is AlH2O6 3+, we know that. So to make a white solid, then it's going to have no charge. Something with no charge is not going to be able to bond to the polar water molecules, and therefore it comes out as a white solid. It's got no charge. So 3 of the waters are turned into OHs, and I make some carbon dioxide, and I'm going to make some water as well. So I've got the H pluses coming off this with some O's to make some water. There's a good chance if you've got H's and O's, you're going to make water. The problem is it doesn't balance. So how do I balance it? Well, the first thing to note is I've got 3 plus and 2 minus. So if I have 2 of these, that will give 6 pluses, and 3 carbonates will give 6 minuses. That's a start. So 2 of these and 3 of these gives 6 plus, 6 minuses. I've got 2 ALs now, so I'm going to need 2 AlH2O3 OH3. I've made 3 Cs, 3 Cs, and then if you have a look at the H's, you can balance up all the H's and you find you need 3 H2Os, or you can balance the O's either way. Aqueous potassium hydroxide is added until in excess to solution Y. 2 observations you will make. Well, first of all, you will get a white solid. That's the same as this, aluminium hydroxide, AlH2O3OH3. That's my white solid. But then with sodium hydroxide or potassium hydroxide, it will redissolve. So it redissolves, the solid dissolves or forms a solution. So let's have a look at the 2 equations now. The OH minuses from the potassium hydroxide react with 3 of the waters come off, and the 3 hydroxides are replaced. So that's going to give this with no charge. Remember, 3 plus, nothing on the water. OH is 1 minus, so 3 1 minuses and 3 plus gives no charge. That's why it's a white solid, because it's got no charge and doesn't bond then. It's not got a charge to bond to the polar water molecules. And 3 OHs then replace 3 of the water ligands, so 3 waters come off. And that's my solid precipitate, my white solid. And then if I add more OHs, another OH replaces an H2O. So one of these H2Os now becomes another OH, so that becomes OH4 and only leaves 2 waters. Now it gets a minus charge. We know it's a minus charge because there's 1 minus on the left, 1 minus on the right, or another way of looking at it is this is 3 plus, no charges on the waters, 1 minus for each of the hydroxide ions, that's 4 minuses, 3 plus, 1 minus, and one of my waters has been replaced by an OH now. This will now redissolve because it's got a minus charge, so it'll form a bond with the polar water molecules. Question 8. This question is about sodium and some of its compounds. Use your knowledge and structure of bonding to explain why sodium bromide has a melting point that's higher than that of sodium and also higher than that of sodium iodide. So you've got to talk about each of these in turn. We've got to consider what kind of bonding's in sodium. So it's metallic bonding. So you've got to describe metallic bonding. So it's got metallic bonding. What metallic bonding happens is the atoms release electrons which become delocalized. So the Na, the sodium, releases an electron, loses an electron, and each of the sodium atoms then become ions, Na pluses, and the electrons are delocalized. So there's an attraction between the Na plus ions and the delocalized electrons. That's a metallic bond. Next, sodium bromide and sodium iodide, they're ionic. So you've got ionic compounds. So what happens is the Na is in group 1, wants to lose 1 electron. Bromide is an ion, a Br minus ion formed from bromine. Bromine's in group 7, wants to gain 1 electron. So the sodium atom gives an electron to the Br. So this becomes Na plus and this becomes Br minus. There's going to be attraction between the Na plus and the Br minus ions. And the similar kind of thing happens in sodium iodide. That becomes Na plus I minus, and they form a giant ionic lattice, a large ionic lattice. So why then is sodium bromide got a higher melting point than sodium iodide? It's got to be something to do with the difference between bromide and iodide, and the difference is Br is smaller than iodide, and so you're going to get the ionic bonds are stronger, or words to that effect, than the metallic bonds. You can say that first of all. and there's a stronger attraction between the ions in NaBr than there is in NaI, and the reason is that the Br ion is smaller than the I- ion. So if the ions are closer together, then you get stronger bonding. Question 8.2. When 250 milligrams, or if you divide by 1,000 to get it into grams, 0.250 grams. Remember, if you go from milligrams up to a higher unit value of grams, you divide by 1,000. Added to 500 centimetre cubed of water at 25 degrees C, a gas was produced. Write an equation. Well, sodium's a metal. With water, it'll make hydrogen gas. So sodium makes sodium hydroxide. A metal and water always makes the hydroxide, unless it's something like magnesium with steam that will make magnesium oxide. But in cold water it makes the hydroxide. I know hydroxide is OH1 minus, Na is Na1 plus because it's in 1 plus oxidation state, it's in group 1, so it's just NaOH, and you make some hydrogen, and you can balance that by putting half H2. Then what happens? So what we've got is we've got Na, we've said we've got 250 milligrams or 0.25 grams. We know the MR of sodium is 23. We can look that up in a periodic table. So moles equals mass divided by MR. Mass is 0.25 divided by 23. So I've got 0.109 moles of sodium. Now, 0.109 moles of sodium will make half the number of moles of hydrogen, because 1 mole of sodium makes half a mole of hydrogen in the equation. So if we divide this by 2, I'll work out the number of moles of hydrogen. So number of moles of hydrogen is this divided by 2. It's 5.43 times 10 to the minus 3. You're allowed up to 4.45 times 10 to the minus 3, so it allows some error on your calculator. Okay. Next thing then, we can use PV equals nRT. We've got a clue because we've got R. So PV equals nRT. What do you need? Pressure has got to be in pascals. 101,000 kilopascals. 101 kilopascals. So to get that down into pascals, then we multiply by 1,000. So a large unit value into a small unit value, you multiply by 1,000. So that becomes 101,000 pascals. We've got to get the temperature into Kelvin. So 25 degrees C, you add 273 to convert degrees C into Kelvin, 298 Kelvin. Now we can use PV equals nRT. Pressure times volume is number of moles, which we've worked out before for the hydrogen. Remember, this is called a gas equation, PV equals nRT. So you've got to have gas. N is the number of moles of gas, the hydrogen gas. Always remember that you're talking about gases when you're using this equation. 8.31 is R, and the temperature is 298. And if you multiply this out and then divide by 101,000, then you work out that V is 1.33 times 10 to the minus 4. Remember, a volume in PV equals nRT is in meters cubed, and it says calculate the volume in centimeters cubed. So meters cubed down into a lower unit value, decimeter cubed, we multiply by 1,000, and then to get decimeter cubed into the next unit down, centimeter cubed, you multiply by 1,000 again. So you're going to multiply this by 1,000 and then by 1,000 again, and it'll come out as 133. They allow 134 as well. Calculate the concentration in moles decimeter cubed of sodium ions in the solution produced. So we know the number of moles of sodium is 0.109. We know that concentration is moles, 0.0109 divided by volume. Volume is 500 centimeter cubed. To convert that into decimeter cubed by dividing by 1,000, a small unit value like centimeter cubed up into decimeter cubed, a large unit value you divide by 1,000 is 0.5. So concentration is 0.0109 divided by 5 times 10 to the minus 3, or 0.5, and it'll come out as 0.0217. They actually allow 0.022 because most of these values are to 3 significant figures. So they allow it to 3 significant figures, except the 25 degrees C is to 2 significant figures. So they allow you to put your answer to either 2 or 3 significant figures. They'll allow both. Sodium reacts with ammonia to form NaNH2 that contains N H2 minus ion. Draw the shape. Well, let's consider nitrogen's in group 5. If it's got a minus, it's got an extra electron, so it's got 6 electrons now. It had 5 because it's in group 5. An extra one means it's got 6. 2 hydrogens come along and form 2 bonding pairs. That means there's 4 electrons left over, or 2 lone pairs. So it's got 2 lone pairs and 2 bonding pairs. It's going to be bent. It's going to look like that. We've drawn them as lobes like this. These are lone pairs. And so if you imagine that you draw them like that, and you might think it's tetrahedral, 1, 2, 3, 4, but it's not tetrahedral. Oh, by the way, we put the minus. We're not quite sure where the minus is, so we draw a square bracket around it and put a minus to say somewhere there's a minus. So I've got 2 lone pairs because nitrogen had 6 electrons, 5 of its own, an extra 1. 2 bonding pairs take up 2 of the electrons, 4 left over, 2 pairs. These are my 2 lone pairs. You might think that's tetrahedral because there's 1, 2, 3, 4 pairs, 2 lone pairs and 2 bonding pairs. Except it's not, because what actually happens is, first of all, you don't actually you don't actually see these lone pairs, so actually you consider this part, which means that it's V-shaped or bent. You actually don't take the lone pairs into consideration when you're looking at the shape of the molecule. You ignore these. You need to consider them to work out what the actual shape is, but you actually only look at the bonding pairs when you're actually describing the shape. So it's V-shaped or bent. And if it were a tetrahedral, something like CH4 with 4 bonding pairs, it'd have a bond angle of 109.5. Every time you replace a bonding pair with a lone pair, you subtract 2.5. So 109.5 subtract 1 lone pair, subtract 2.5 becomes 107. That would be something like ammonia with NH3 with a lone pair. Or if you have a second lone pair, then you take off another 2.5, so it becomes 109.5 down to 107 down to 104.5. What's the justification for it coming down to 104.5? Well, you need to talk about the electron pair repulsion theory. You need to say that electrons repel. Electron pairs repel and go as far apart as possible. That's the first part. And then you talk about the fact that lone pair repulsion is bigger than lone pair bonding pair repulsion, which in turn is bigger than bonding pair repulsion. And that's all you need to say. Question 10. A student added 625 milligrams, or 0.627 grams, of hydrated sodium carbonate, and it gives you the formula Na2CO3 XH2O. Doesn't tell you what the X is. Maybe we've got to work that out. To 200 centimetre cubed of 0.25 mole hydrochloric acid. This gives me a clue. I've been given a volume of hydrochloric acid and a concentration. It wants me to work out moles. Let's do that first of all. Concentration 0.25 equals moles divided by volume, but the volume's got to be in decimeter cubed, not centimeter cubed. So centimeter cubed up into decimeter cubed, up into a higher unit, a larger unit, divide by 1000, 0.2. So 0.250 equals moles divided by 0.2. Moles is 0.250 multiplied by 0.2, which will work out as 0.05. I do the same now. So I do the same now for the sodium hydroxide, just simply because I must have to. I've been given 0.150, a concentration of sodium hydroxide, and a mean titration volume for the sodium hydroxide. I must have to do the same. Concentration 0.15, volume 26.6, divide by 1000 to get it into decimeter cubed, 0.0266. Concentration 0.150 equals moles divided by 0.0266. So moles are these two numbers multiplied together. Moles is 0.150 multiplied by 0.0266 decimeter cubed. 3.99 times 10 to the minus 3. Now, sodium hydroxide and hydrochloric acid react in the ratio 1:1. HCl plus NaOH will make water, H2O and NaCl, 1:1. So the NaOH used in the titration is 3.9 times 10 to the minus 3. So the number of moles of acid needed is 3.9 times 10 to the minus 3. Okay. However, if we're talking about the whole sample, we've taken 25 centimeters cubed portions of the sample, and the whole sample, the whole solution, was 250 centimeter cubed. So we have taken a tenth of it. 250 divided by 25 is 10. We've taken a tenth. So we've worked out how much hydrochloric acid was left over in the 25 centimeter cube sample, but we need to times by 10 to work out how much hydrochloric acid was left over in the 250 centimeter cubed sample. 3.99 times 10 to the minus 2. Okay, so 3.99 times 10 to the minus 2 moles of hydrochloric acid were left over in this 250 centimeter cube sample after I've reacted the hydrochloric acid with this. So I started with 0.05 moles of hydrochloric acid and I've ended up with 3.99 times 10 to the minus 2 moles of hydrochloric acid. Why has the hydrochloric acid gone down? Because that's how much I started with and that's how much now I've got. The reason is it's reacted with the sodium carbonate. So the hydrochloric acid has reacted with the sodium carbonate, then it's been titrated with sodium hydroxide to find out how much hydrochloric acid has been left. So if I subtract the two, the amount of hydrochloric acid that I started with and the amount of hydrochloric acid that I've ended up with, it ends up as 0.101 moles. So surely now I can use the 0.101 moles of hydrochloric acid that's reacted with the sodium carbonate to work out the number of moles of sodium carbonate. If 1 mole of hydrochloric acid reacted with 1 mole of this sodium carbonate, 1:1, the amount of sodium carbonate would equal the amount of acid that's reacted. But 2 moles of acid react with 1 mole of sodium carbonate. I know that because it's going to make sodium chloride, and I've got sodium chloride is NaCl, and I've got 2 NAs here and 1 Cl. So 2 moles of HCl will react with 1 mole of sodium carbonate. Or we could say 1 mole of hydrochloric acid reacts with half a mole of sodium carbonate. So this is the amount of acid that's reacted with the sodium carbonate. If I divide it by 2, it will tell me the amount of sodium carbonate that I've got in there, because 2 moles react with 1, or 1 mole reacts with half a mole. So now I know the number of moles of sodium carbonate that I've got, 5.05 times 10 to the minus 3. I also know the mass of sodium carbonate that I've got, 627 milligrams. Milligrams into grams, going up into a larger unit value, I divide by 1,000, 0.627 grams. Then moles equals mass divided by mR. Moles of sodium carbonate is 5.05 times 10 to the minus 3 equals the mass divided by the mR. The mass is 0.627. So 5.05 times 10 to the minus 3 equals 0.627, the mass, divided by the mR. With a little bit of rearranging, the sodium carbonate, the mR is 0.627 divided by 5.05 times 10 to the minus 3. It's that value there. That's the mass of the sodium carbonate, XH2O. If from that I subtract 106, That's the mass of 2 NAs at 23 each, 1 C at 12 and 3 O's at 16 each. It tells me how much of the mass is at XH2O. So if I take away 106, it comes out as 18. Now the MR of a water is 2 H's, 2 1's and a 16, which is an 18. So the MR of a H2O is 18. I've got 18 left over. 18 grams left over. So an MR of 18 left over. The MR of a water is 18. So it means that I've got 1 water in there and X is 1. Question 9. Quite a tricky question this. It's about vanadium compounds and ions. Use the table 4 to identify a species that can be used to reduce VO2+. There's VO2+ at the top with an electrode potential of 1. Used to reduce VO2+ ions to VO2+. Yeah, that's the top one. Electrode potential 1. And no further. So first of all, you've got to decide which of the other ones, which of the other equations could make this reaction happen, this top one, with an electrode potential of 1. Well, if this one's going to go ahead in this direction and have a positive electrode potential of 1, the other ones combining with it would go the other direction. Yeah. So there's electrons on this side, on the left-hand side of this one. This is reduction. These would have to be turned into oxidation and go the other way around, and these figures would become minuses, or this one will become plus. So this one, and say for example this Cl2 plus 2 electrons 2 Cl minus, would be plus 1 for this one in this direction, reduction, and this one will be forced into oxidation, minus 1.36. Plus 1 minus 1.36 is minus 0.36, so that wouldn't go ahead. So it can't be this one. In other words, you're looking for something with an electrode potential lower than 1. All the others could feasibly work, but Cl2 plus 2 electrons to 2 Cl minus will not combine with that top equation and make that top equation go in that direction, so that VO2 plus is reduced. All of the others would do, because if we make all the others minuses, or this one minus minus a plus, when we add these on, this overall 1.00 is bigger than, say for example, plus 0.77. So this one could go in the other direction, minus 0.77, add 1, still gives plus 0.23. It's still a positive value, and this one would go ahead. Okay, but the question is, which of the others is it? Okay, it says and no further, and no further. So when you make VO2 plus here, it could react again. VO2 plus 2H plus an electron goes to V3 plus an H2O. It could do this one. So we want this one to go ahead with an electrode potential of 1, but this one not to then go ahead with an electrode potential of plus 0.34. Your answer is Fe3 plus an electron goes to Fe2 plus. This is your equation here. That one will do it. Let me explain why. Plus 0.77, we're going to force it to go in the backward direction, so it becomes oxidized rather than reduced. So this one can go in the forward direction. Plus 1, take away 0.77 gives plus 0.23. So this one goes ahead. Will this second one go ahead? Plus 0.34 minus 0.77 gives a minus value, because this is bigger than this one. so the second one wouldn't go ahead. This one wouldn't be reversed and go in, wouldn't be an oxidation reaction. It wouldn't go right to left. It would continue to go left to right, because otherwise, if this one went ahead and this one went backwards, it would give a negative electropotential. Okay. So my answer is the reagent that can be used is Fe2+. That can be turned round and make Fe3+, because the electropotential of VO2+ is 1. The electropotential of VO2+ is plus 0.34. And the electropotential of Fe3+ to Fe2+ is 0.77. It's less than 1, 0.77. So if you combine those two, 1 take away 0.77 is 0.23. So this top one goes ahead. But it's larger than plus 0.34. 0.77 is larger than plus 0.34. So if you reverse it around the other way and it becomes minus 0.77 plus 0.34, you're going to get a minus 0.43. And that's not going to go ahead. Question 9.2. Give the oxidation state of vanadium in VOH2O6 2+. Well, the waters are neutral. The O is -2 oxidation state, because it's in group 6, going to gain 2 electrons to fill its outer shell, -2 charge, -2 oxidation state. So something, an oxidation state of the V, -2 gives +2 overall. So your answer is 4, because 4 minus 2 is +2. This VH2O4 Cl2 plus ion has 2 isomers. One isomer is shown. Draw the structure of the other isomer and state its type of isomerism. Well, what we've got is, we've actually got geometric isomerism here. We've got here the 2 Cl's with a bond angle of 90. They are together on the same side. Z isomers. However, if they were opposite, either there and there, or here and here, they would be opposite each other and have a bond angle of 180. So this way, they are Z isomers opposite each other, either there and there, or here and here, or even here and here. They will be opposite and they will be E isomers. So I've drawn another one with 2 Cl's opposite. Now I've moved the Cl from here to here, so they're opposite. You could have had the Cl up and down as well, either way you wanted to, as long as they're opposite. And the type of isomerism is geometric isomerism. You can also call it cis-trans or EZ, or even just say it's stereoisomerism. Stereoisomerism means that you've got the same structural formula but different positions of atoms in space. It also includes optical isomerism. Heating VH4VO3 produces vanadium 5 oxide, water and another product. Well, we need to decide what V5 oxide is. Vanadium is an oxidation state +5. Oxygen, O, is an oxidation state -2 because it's in group 6, going to gain 2 electrons. So I've got a 5 oxidation state and a 2 oxidation state. So let me do spoilers and show you what vanadium 5 oxide is, and you'll understand. It says here NH4VO3 makes, this is vanadium 5 oxide. Let me explain how I've come up with that then. We said oxide, the O is -2 oxidation state. The V is in 5 oxidation state. So we've got to get those two to balance to have no charge left over. 2 5s are 10, 5 minus 2s are 10. So 2 plus 5s gives +10 oxidation state here. 5 minus 2s gives -10 oxidation state and leaves no charge left over. It also says it makes water, And then you've got to work out what you've got left. Well, you've got some N's that you've not used, and you've got some H's that you've not got used, so it makes ammonia. Okay, you probably have to work that out, something with N's and H's in it, and then you can balance it. You're going to need 2 V's, so you're going to need 2 in front of the NH4VO3. That means you're going to need 2 N's or 2 NH3s to balance it up. Vanadium 5 oxide is the catalyst used in the manufacture of sulfur trioxide, SO3. Give 2 equations to show how the catalyst is used and regenerated. So we use V2O5 is used in the manufacture of sulfur trioxide from SO2. So sulfur dioxide makes sulfur trioxide, V2O5. The only other oxidation state that we know of as an oxide is vanadium 4. 4 minus 2s for the oxygens, minus 2 oxidation state for an O, remember, because it's in group 6, gains 2 electrons, 2 minus charge, so 4 minus 2s is minus 8. So 2 4s, that's in oxidation state, plus 4, 2 V's. So that's vanadium 4 oxide. Now then, this V2O4, it says the catalyst is regenerated, the vanadium 5 oxide is regenerated. So it's going to be remade from V2O4, which is made. So the V2O4 reacts with more oxygen to remake the V2O5. Question 4.8 is about a barium ion, a barium 1+ ion with a mass of 137. And what does it tell you? Kinetic energy equals half mv squared, where mass is the mass of one particle in kilograms, v equals the speed. You've got Avogadro's constant, so you're obviously going to use that to work out the mass of one particle. So what have we got? We've got kinetic energy. Yeah, we're given the kinetic energy. 3.65 times 10 to the minus 16 equals half m. M is the mass of a particle. Well, 137 of a barium particle is the mass of 1 mole. If I divide the 137 by Avogadro's constant, I'll find out the mass of one particle. That'll be in grams. I'll have to get into kilograms. So grams into kilograms, I'm going to have to divide by 1,000 because that m there is the mass of one particle in kilograms, and then that'll give me v squared. I can square root it and find out v, and from that I can work out the length of the detector. So let's have a look then. Kinetic energy equals half mv squared. That's my kinetic energy I've been given, equals half mv squared. Just to simplify, I'm going to multiply everything by 2. So 7.3 times 10 to the minus 16 equals mv squared. The mass of 1 mole of 137 barium is 137 grams. It needs to be, this m value is in kilograms, so I'm going to divide by 1,000. Remember, a small unit up into a large unit, you divide by 1,000. So the mass of a mole is 0.137. I know the number of particles in a mole is Avogadro's number, so if I take this mass of a mole and divide by Avogadro's number, I'll work out the mass in kilograms of one particle, which is 2.275 times 10 to the minus 25. So I can put that in as an m value now. So I've got my kinetic energy, or twice my kinetic energy. 2 lots of kinetic energy equals the mass multiplied by v squared. So v squared equals 7.3 times 10 to the minus 16 divided by the 2.275 times 10 to the power 25. V squared is 3.2088 times 10 to the power of 9. I square root it, and V is 5.6646 times 10 to the power of 4. Now velocity is distance divided by time. You'll know that speed is distance divided by time because you go, say for example, the speed of a car might be 30 miles per hour. So distance, miles, time, hour, per means divide by. So speed is distance divided by time. I've got my v, I've got my speed, my velocity or speed, 5.6646 times 10 to the power of 4. I've got my time, it gives me my time in the question, which is 2.71 times 10 to the minus 5. there. The ion takes 2.71 times 10 to the minus 5 to reach the detector. So I multiply these two numbers together and my distance is 1.53 and it's in meters. A-Level Paper 1, June 2018. Complete the Born-Haber cycle. So what have I got? I've got magnesium solid, staying as magnesium solid, half a mole of O2 gas going to O, so breaking the bonds, so enthalpy of bond dissociation or enthalpy of atomization. Magnesium solid going to magnesium gas, so enthalpy of atomization. Then what's going to happen next? Well, the next one that's endothermic is going to be the first ionization energy of magnesium to form Mg+, an electron, and the O gas stays the same, so you only change one thing at one time. So I'm changing the magnesium and the O is staying the same. The next one is another jump, Mg+ going to Mg2+, and an electron, so the second ionization energy of magnesium, and I've got one that comes down here. This is the first electron affinity of oxygen. So the O atom, the oxygen atom, gains an electron to form O-. There's still one electron left over, and this is the second electron affinity where it gains the second, where the oxygen atom gains the second electron to form O2-. And then we've got the lattice enthalpy here, where we've got gaseous ions forming 1 mole of a solid lattice, ionic lattice. I've put them into the diagram here so you can see what's happening. So I've got minus 602 will be the enthalpy of formation of magnesium oxide. So enthalpy of formation is forming the magnesium oxide from elements in their standard state. So magnesium is a solid metal in its standard state. Oxygen is a gas. Remember, standard state is how you'd find them in a laboratory. And then I've put oxygen going from oxygen O2 to half a mole of O2 into O, and I've cut, that's the bond dissociation enthalpy of oxygen, so that's a 496 here. And then we've got magnesium atomization, magnesium solid going to magnesium gas, so that's 150, so enthalpy of atomization of magnesium. Then we've got here, up to here was the first ionization energy of magnesium, which was a 736. We've got the second ionization energy of magnesium, a 1450. Then we've got the first electron affinity of oxygen, a minus 142, so it comes down. And then we've got a plus 844. The second electron affinity is endothermic. And then we've got the lattice enthalpy coming down here. So what am I going to do? If I start from here and come down here, this is the missing enthalpy change that I need, coming from magnesium, Mg2 plus gaseous ions and O2 minus gaseous ions to form 1 mole of a solid ionic lattice, MgO. So I want it to come from here to here. So let's go from here to here is not plus 844, it's minus 844 because the arrow is going in the other direction. And then to go from here to there, the arrow is going the other direction. It's a plus 142. Come down here, it's a minus 1450, a minus 736, a minus 150, a minus 496, and this one's going in the right direction, a minus 602. So when you add all of those up, it turns out as minus 3888 kilojoules per mole. Question 2. Nitrogen and hydrogen were mixed in a 1 to 3 mole ratio, so there's 1 mole of nitrogen for every 3 moles of hydrogen, and left to reach equilibrium. When equilibrium was reached, the total pressure in the flask was 150 kilopascals, so all the gases contribute towards 150, make a pressure of 150 kilopascals, and they're all contributing. The mole fraction of NH3 in the mixture is 0.8. So that means the other two gases, the nitrogen and the hydrogen, must be making a mole fraction of 0.2. So the mole fraction of the NH3 is 0.8, so by subtraction, the remaining gases, the N2 and the H2, must make a mole fraction of 0.2, the remaining part of the fraction, so that 0.8 and 0.2 adds up to 1. We know that 1 out of 1 to 3 or 1 out of 4, a quarter is nitrogen, and 3 out of the 4 are hydrogen, because the ratio is 1 to 3. So the mole fraction of the nitrogen there is a quarter of the remaining 0.2, and the mole fraction of hydrogen is 3/4 of the remaining 0.2. So I've multiplied that out, and therefore the partial pressure of the nitrogen is its mole fraction 0.05 multiplied by the total pressure 150, that's 7.5 kilopascals. The partial pressure of the hydrogen is its mole fraction 0.15 times the total pressure 150 kilopascals, which is 22.5, and the partial pressure of the ammonia is 0.8 multiplied by the total pressure 150 or 120 kilopascals. Give an expression for the equilibrium constant Kp. So it's the partial pressure of the ammonia, which is on the right hand side, squared, divided by the partial pressure of the nitrogen, divided by the partial pressure of hydrogen to the power 3. So it's very similar to a Kc, an equilibrium constant, but instead of using concentrations, using partial pressures, because a partial pressure is effectively the concentration when you're talking about gases in a system. In a different equilibrium mixture under different conditions, the partial pressure is shown below. Calculate the value of the equilibrium constant Kp. So I'm just putting these numbers in really. So I've worked out my Kp here, and I'm just putting the partial pressure of the ammonia squared divided by the partial pressure of the nitrogen, and that divided by the partial pressure of the hydrogen to the power 3. So I'm just putting those numbers in. And when you put those numbers in and calculate it, it comes out as 0.0029. They allow anywhere between 0.0029 and 0.0030. Calculate the units. Well, on the top I've got kilopascals multiplied by kilopascals, and on the bottom I've got kilopascals multiplied by kilopascals multiplied by kilopascals, 3 of them, and another kilopascals on the bottom. So I've got 2 kilopascals on the top, 1, 2, 3 kilopascals on the bottom, and another one, a fourth one. So 2 of those cancel, so I've got 1 on the top and kilopascals on the bottom. That's kilopascals squared, 1 divided by kilopascals square, or you could say kilopascals to the minus 2. The enthalpy change for the reaction is minus 92. So going in the forward direction here, so when nitrogen and hydrogen make ammonia, then it's minus 92. Minus 92 is an exothermic reaction, so when the nitrogen and hydrogen make ammonia, it gives out 92 kilojoules per mole. It's exothermic. So if I increase the temperature by Le Chatelier's principle, the reaction will try and lower the temperature of the system. So if I increase the temperature by Le Chatelier's principle, it will oppose that and try and lower the temperature. So it's not going to go to the right hand side, because going to the right hand side it's exothermic and gives out heat to the system. It's going to go to the left hand side. So it's going to decrease. If it goes to the left hand side, then these values on the top, the ammonia decreases, because you're making less and less ammonia, you're making more and more nitrogen and hydrogen if it's shifting to the left hand side to try and lower the temperature. So you're making more nitrogen and hydrogen and less ammonia. So if you're making less ammonia and more nitrogen and hydrogen, the numbers on the bottom are going up and the number on the top is going down. So the Kp decreases, and the way to explain that is the reaction's exothermic, gives out heat in the forward direction. Increasing the temperature by Le Chatelier's principle is going to try and oppose that change and lower the temperature, and it can do that by shifting the position of equilibrium. It should say shifting the position of the equilibrium to the left hand side, because going to the left hand side it's endothermic and takes in heat. Question 3. We've got a reaction going on between ammonia and oxygen. 4 moles of ammonia and 5 moles of oxygen make 4 moles of nitrogen monoxide, NO, and 6 moles of water. We've got some entropy values. Calculate the entropy change for the reaction between ammonia and oxygen. Well, first of all, you need to remember that the entropy change is the sum of the entropy of the products minus the sum of the entropy of the reactants. So what you've got to do is, so the entropy change is 4 multiplied 4 NO, so 4 times 211, and then 6 times water is 6 times 189, so it's 4 times 211, add 6 times 189, that's the sum of the entropy of the products. Take away the sum of the entropy of the reactants. The reactants is 4 lots of NH3, 4 times 193, and 5 times 205. So you calculate this, the sum of the entropy of the products, and you take away the sum of the entropy of the reactants, and it equals 181 joules per Kelvin per mole. You know it's in joules because that's in joules per Kelvin per mole, so it's in joules. If it asks for it in kilojoules, you'd have to divide that by 1,000, and it would be 0.181. Remember, joules into a higher unit value like kilojoules is a divide by 1,000. Calculate a value for Gibbs free energy change, delta G, in kilojoules per mole now, so we are going to have to convert that to 0.181 kilojoules per mole. For the reaction between ammonia and oxygen at 600 degrees C. So let's have a look at the equation. Delta G equals delta H minus T delta S. So Gibbs free energy change, delta G, is the enthalpy change. The enthalpy change is minus 905. Take away the temperature. Now the temperature is 600 degrees C, but it needs to be in Kelvin, so you need to add 273 on. So that's 873 here. So it's take away 873, and the 873, the temperature, is multiplied by our entropy change, which is 0.181, because that's in kilojoules per Kelvin per mole. So you need to get that into kilojoules rather than joules. So when you work that out, it equals minus 1063. They allow you anywhere between minus 1063 and minus 1060. The reaction between ammonia and oxygen was carried out at a higher temperature. Explains how this affects the value of delta G. Well, if this is at a higher temperature here, minus T delta S is going to be more negative, or T delta S gets bigger. T delta S gets bigger, so minus T delta S is getting bigger, more negative, and so delta G will be getting more negative. Platinum acts as a heterogeneous catalyst. Heterogeneous means it's in a different phase, it's in a different state. So it's going to be solid, and the ammonia and oxygen are gases. So you've got something that's solid and maybe something that's gases, two different states. And it provides an alternate reaction with a lower activation energy. So what it does is it brings the particles together. So it binds or bonds the particles to its surface. That brings the particles closer together so that they can react, and then it releases them. So the reactants are bonded onto the platinum surface, a process called adsorption. They react on the surface because they're closer together, and then the products are released, a process called desorption from the surface. But you don't need to use those words. You can just say that the reactant bonds onto the platinum surface, they then react, and the products are then released from the surface. Deduce the change in oxidation state of nitrogen when NH3 is oxidized to NO. Well, hydrogen's in +1, and there's 3 of them. There's no charge overall on NH3. So 3 + 1 is +3, so the nitrogen must be in -3. So the -3 and +3 equals 0 because there's no charge. Oxygen is -2, it's in group 6 of the periodic table, gains 2 electrons, 2 minuses. There's no charge left over, so that's +2. So it goes from -3 to +2. When ammonia reacts with oxygen, nitrous oxide N2O can be produced instead of NO. Give an equation for this reaction. So I'll have ammonia and oxygen making N2O. What else might be formed? Well, I've got some hydrogens and some oxygen, so it's a good bet it's water. And then I've got 2 N's here, so I need 2 NH3s. That makes 6 H's here, so I need 3 H2O's. 1 add 3 is 4 oxygen, so I need 2 O2.